record this, so those out in the studio audience. Okay, kids. Wow. Okay, a couple of things on when you send me your stuff from that Cam Scanner app. Try and send that from your school email address, okay? Because that's going to make it easier for me than if I have to reply back to it or if I have to track that down. I have your school email address in my contact list, but not your personal email. And so if you can send it from that, that's going to make life simpler. Okay. So hopefully, let me see. I've got to keep track of which group I'm going to be with. Okay, so hopefully you guys have gotten the emails with two different video YouTubes, one for the MKS system, one for dimensional analysis. You should have the dimensional analysis worksheet. So that's going to be due on Monday. So here's what's going to happen. So starting next week, okay, here's the decision that you all need to make on Monday, because I won't see you all again until Tuesday, okay? So on Monday, the other group is going to be here, and here's what's going to happen. I'm going to say, hey, does anybody have any questions over the dimensional analysis or the lab? Okay, because those two things are going to be due on Monday, even for you guys. Okay, those two assignments are going to be due on Monday. So what you all have to decide is that, are you guys going to zoom in and watch like the live broadcast first block? I'm also going to send out, this mask sucks. It just like keeps sliding down. That's another thing I didn't think I'd have to worry about. Gee, which mask am I going to wear when I teach? Let's try this one. Okay. So you can watch first block. I'll have the meeting open. I'm going to have somebody sitting here. You can just, I'll let you in. Okay, that's an option. If you're a late riser, I'm going to send you the link in Google Classroom where you can actually watch my third block class, okay, which does can start like at 11:45, so that's an option. Or I'm going to record the Zoom meeting and dump it out on YouTube and you can watch it then, okay? So I don't care which option that you pick, okay? Zoom in first, zoom in third, watch it on YouTube. But I want, for you guys, I want that assignment by 5 o'clock on Monday. So don't think, oh, I'll just watch the YouTube video Monday night, okay? Oh, let's make it 6 o'clock, because realistically, I won't start grading until then anyway. Let's make it 6 o'clock. So for you guys, those two assignments, the lab that you're going to do today, and that dimensional analysis, and send them as separate entities. Do not lump them all together, okay? Send them, here's the lab, here's the dimensional analysis sheet. Do not send them as one big document. So you can have those two things to send it separately. Make sure you put, hey, you know, here's your last name, dimensional analysis. Here's last name, spring lab. Make sure that you've got those. So I don't care how you, but so if you have questions, the ability to zoom in, you can, in the chat, you can say, hey, because I'm going to have somebody watching that computer. So they're going to be able to say, hey, you know, tell Burkamp to explain number 4, okay? Or on the lab, hey, I don't understand the question about how the slope changes on the moon. So if that's something that you want me to explain, and that's the advantage of zooming in, because then you can throw a question out on the chat. The moderator will get that to me. I'll be able to say, hey, you know, Addie's got a question on number 3. She wants you to explain that better. So that's the advantage of it. Okay. So hopefully by now, if you've watched that lecture on the MKS, we've got 3 big units that we use. Meters, kilograms, and seconds. Okay? So that's the video that hopefully you all have and you watch. So these are what we call the 3 fundamental units. And then from that we can get meters per second squared, and kilograms meters per second squared, otherwise known as newtons. So the beauty of physics is that these 3 units here of mass, meters, kilograms, seconds, and velocity, acceleration, and force. These are the ones that we will not introduce any new units, and probably until like November or probably December when we get into energy. Okay, literally everything that you're going to deal with between now and probably the first week of December, it's going to be this. Okay, that's it. There's nothing else. So it isn't like we talk about these units on the very first day and we never talk about them again. Okay, it's very sequential. It builds off each other. So, like in the lab today, you're going to be dealing with meters, you're going to be dealing with kilograms, you're going to be dealing with force. Now, on that dimensional analysis assignment, let me point out the two things that notoriously go wrong. So, if you haven't watched that, when you do dimensional analysis, and this is going to be what you're going to do on the lab today when you find the slope of the line. Let's say, for example, in an equation, you're going to multiply velocity by time. So here's your process. You come in here and you say, oh, velocity, that's meters per second. Time is in seconds. The seconds cancel out. I get meters. So when you're doing dimensional analysis, and you'll see me say this on the video, if you can stack these vertically, it's easier to see what's going to happen as far as things canceling out. If you write these like in a horizontal line, if you write it like this, where you go, oh, that's meters per second times seconds. Visually, what I found over the years is if you write it like this, then you tend to think that seconds times seconds, and you go, oh, that's meters per second squared. For whatever reason, your mind understands this better if you stack these and then see that they cancel out. You don't have to, but I'm just saying. Could potentially avoid some mistakes. Now, that's velocity times time. So if I multiply a velocity by some amount of time, I get meters, which is a distance. Don't confuse this meters with that m and F equals ma. So this as a unit is going to be a distance. If you see F equals ma, or whenever you see mass, that's going to be in kilograms. So don't confuse m as a unit with m as a variable for mass. It happens a lot. Don't do that. Now, here's the other thing that we'll do a lot. We're going to take like change in velocity and divide that by time. And this will allow us to get acceleration. So acceleration is just a change in velocity. Could be speeding up, could be slowing down, could be changing direction. So when you do this, and you do dimensional analysis, that's meters per second divided by seconds. And here's what I have to stress about dimensional analysis, is that it's a process, okay? It's not about getting an answer. So that's the other thought process shift that you need to make to be successful in this class or any difficult class. Unfortunately, for 12 years, if you can...
Wave the magic chicken.
Yeah? Hold on. She's going to try and wave the magic chicken.
This has to be on.
I did that. And like if I play a video out of that, it runs, huh?
This is dead.
No, it's not.
It's not turning on.
Just,
Okay. I lied, it's not.
these young kids, wow, cheeky.
Maybe us little dogs can learn something.
Yeah, no.
Make it look like we are.
It's picking up.
Did
sound.
okay.
Oh, wait, I guess I should apply that, huh? Can you see? I can see everything I'm doing right
Yeah.
now.
Yeah, it's starting to work. We just gotta crank up the volume. Okay, that's 100.
These are cranked.
Well, it's hearing the microphone. The
Oh,
computer's
it's not plugged in here.
Oh, Steve.
It was.
You have to plug it into the headphones on the USB thing. I got you this.
Okay.
Yeah, there's on this thing, you gotta plug your speakers into where it says headphones on this thing.
Oh, I was plugging it into,
I know.
Now, your
Got
video
you.
may not work,
It's okay.
okay.
Stan.
Hello. Hello.
Let me go back to your meeting. There you go.
Thank you.
You're welcome.
It's like a kid on Christmas.
Don't discount that. Do not discount how much, yeah. Okay. We're trying to do this. Can you hear it? Okay. We'll see how this works. Okay. You like it better with just me talking or with that?
I like
It's a
it.
little loud.
Yeah.
Maybe try move it out just a little bit.
How's that?
Oh, that's better.
That's good, yeah.
Okay. Because now I don't have to yell, and I'm not going to be exhausted at the end of the day. Okay. So back to our story. And you're going to do this a lot. We're going to spend an entire unit calculating acceleration, okay? So when you do this, and you're doing dimensional analysis, it is a process. It is not a product. But here's the problem. 12 years, this is where the education system has failed you. You've been taught, hey, find the answer. Did you choose C? Did you write down 12? Okay? And that's what you've been trained to do for 12 years, is to get the answer. Life, relationships, upper level science classes, all demand that you focus on the process, not the product, okay? And as soon as you make that shift that says, wow, I'm going to focus on the hard work to get through the process, the product will take care of itself. But the problem is that everybody just wants to focus on the product. I just want the answer, okay? I don't care how I got it, I just want the answer. That isn't how life works. The sooner that you begin to pay attention to the little things in life, okay? Well, no matter what that is, that's when you're going to be successful. Because no boss in the world is going to trust you with big projects if you can't handle little projects, okay? Life lesson number one. So, when you look at this process, changing velocity and dividing it by time, if you shift that and go, okay, I'm going to take meters per second, and instead of dividing by seconds, I'm going to multiply by the reciprocal, and I'm going to get meters per second squared. So, I promise you, these are the two mistakes you are going to make most often. You're going to multiply velocity by time, and you're going to try and get an acceleration. Or you reverse it, and you look at this, and you take velocity and divide it by time, and you think that the seconds cancel out, and then you get meters, okay? Those are the two mistakes that are made most often. So make sure when you take velocity divided by time, you get an acceleration. But if you multiply velocity by time, you get a distance, okay? Make sure that you keep those two things straight. All right. So, on the lab, we're going to deal with independent and dependent variables. Okay? Now, I'm guessing back, even as far back as maybe like 7th, 6th grade, you all were taught about independent and dependent variables. If you don't, if you've forgotten, right, it's like, wow, I have slept since then. I have no recollection whatsoever. So, okay, not a big deal. Now, these definitions are on the back of your lecture notes, okay? So don't worry about writing it down. But we do need to discuss very briefly how I view what you write down. I am not going to grade your notebooks. I have 1,000 things to worry about. Microphones, iPads, just the technology to teach. What you have in your notebook, no offense, is not on my radar screen. So, if you write this stuff down, great. Personally, I always learned better when I had the chance to write stuff down and I could put it in my own words. Some people learn better if they just focus on what's being said and they can remember it that way. I don't care, okay? It's up to you. But there is one caveat. Eventually, we're going to start working some pretty big, complex problems, okay? It'll take me like this entire screen to fill up. So let's say I work this big problem, and then you come up to me and say, and you don't write anything down, okay? You don't write anything down, you just sit there. And then you come up to me and you say, hey, Mr. Urkamp, I don't quite understand how to work this problem. And I'm going to ask you, hey, Sproles, did you write anything down? And he goes, no, Mr. Urkamp. And so maybe once or twice, I'll take pity on his soul, and I'll still help him out. But if he continues to sit there and not write anything down, this isn't going to happen, okay? I'm going to lose patience, because it's like, okay, you won't put forth the effort to write stuff down, but then I've got to come back and reteach you this problem, okay? What you write down, how much you write down, that's up to you. But I will lose patience if you refuse to write anything down and then expect me to rework that problem, okay? It's a little sketchy. All right. So, anybody remember the difference between an independent and dependent variable? Scrolls.
Independent can like change on its own, dependent has to have an independent variable to be able to change.
Kinda. Okay? So, this is the most cyclical definition I will ever give you. So, with your independent and dependent variable, your independent is the one that you control. Okay? That's the one that you manipulate. And your dependent variable, and this is where it's like a cyclical definition. Your dependent variable is dependent upon changes in your independent variable. Okay? So, let's talk about where you're going to graph these. Your independent variable, when you draw a graph, and you all are going to draw a lot of graphs. Your independent variable is going to go here, and your dependent variable is going to go there. Okay? Got that. So let's look at this at an example. Ismail, what would be your dream car? Hold on. The bat phone is ringing. Hello. Yes. 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 Okay, bye-bye. Okay, Ismail, you need to go to the library. Before you do that, what's your dream car?
BMW M3.
Okay, all right, BMW M3. Okay, got it. We're going to use that as an example. Yeah, go down, that was them, run down to the office, or excuse me, down to the library, they have something for you. I don't know what it is, let's just go for that. Okay. Mic'd up again. Okay. So, Ismail, BMW M, okay? So, we're going to look at the BMW M, and we're going to look at two things. We're going to look at velocity and stopping distance, okay? So what we're going to do is we're going to have Ismail maybe go up to 10 meters per second. is gonna hit brakes, and we're gonna measure how far it takes for the car to stop. Okay? And it might be 3 meters, I'm just making up a number. And then it might go 20 meters per second. And then we're gonna see how far it stops, and that might be like 8 meters, okay? So we have two things. We have velocity and we have stopping distance. Which one is my independent variable?
Velocity, right?
Why?
Because like you can change the speed you're going, but then like you can't change like how fast your car stops.
Okay? Or your stopping distance is dependent upon your velocity, right? Or you can look at it as you control how fast you're going. That's what you're controlling, okay, in this process. So velocity is going to be our independent variable, and distance is going to be our dependent variable. We control our velocity, and our stopping distance is dependent upon that velocity. So if we were to draw this graph, so we're going to put velocity here in meters per second. And then we're going to have, that was all D. Distance here. So one of the things you want to be able to do when you start a graph, and this is going to play out in the lab that you're going to do today too, ask yourself, is this graph going to go through the point 0, 0? So here's my question. If we plot the stopping distance of the BMW M versus distance, will this graph start at 0, 0? Man.
Yes.
Yes. Why?
Because if you're not going anywhere, you're not gonna have a stopping distance.
Yeah, if I'm not moving, I got a stopping distance, okay? So we know this graph is going to start at 0, 0. Okay, that's where it's going to start. So what's it going to do from there?
If the velocity goes up, the distance will go up.
Okay? So it's kind of this 70s disco move. So we're going to have something like this, right? A direct relationship. And it could be a linear relationship. And we could express that using y equals mx plus b. It could also be like a quadratic, where it could be y equals kx squared. These are the two that you're going to see most often in terms of the direct relationship in this class. These are without doubt the two you will see most often, right? And you got to get used to the terminology. So if I say it's a direct relationship, all that is meaning is that as one number gets bigger, so does the other. But it could be a direct linear relationship, or it could be a direct quadratic relationship. Y'all have graphed these hundreds of times in your math classes, okay? They're both direct. This is just linear. This is going to be quadratic. But no matter what, as the velocity gets bigger, the stopping distance gets bigger. So based upon this graph, why do they make you slow down to 20 miles per hour in the school zone?
Because there's a certain distance that you would have to be able, like, your car has to have time to stop.
Okay. Now, you're right, you're 95% right, but you mentioned time, okay? Time isn't here. It's going to stop at a certain amount of distance, okay? So when you're talking about what you have on your graph, okay, time isn't here. You can say, if I slow down, I can stop in a short enough distance, okay? That's why this graph is why they make you slow down in school zones. So if Timmy runs out into the street, you have time or a distance to stop before Yeah, Timmy. And by the way, you're going to hear me use Timmy a lot, okay? I can explain all of, like, in chemistry, I can teach you all of gas laws and thermodynamics using a room full of first graders named Timmy. I would never teach them. God forbid I ever teach in grade school. Bad things are going to happen. Little ankle biters. Someone is going to cry by the end of the day. Either them or me. I'm not sure. Probably them. But this is, I don't even like freshmen, for God's sake. Okay. So, no, it's true. There's like three things that I hate. And you'll see that there's three things that I really don't like. And they all start with F form. Freshmen, fractions, and frizzies, like on the side of the paper, like you can have like a spiral notebook and you pull that out into frizzies. Don't like any of it. Okay. Fractions are necessary evil. Freshmen, instead of the verbiage is still out on this. Now, let's say that instead of this, it's not, but let's just play the what if game. What if, when we did this data, it was actually this curve? What would that, well, physically, what would this curve mean?
Your car can really not break at all. Like,
No, not really. If this was the line, okay, the faster you go, what would happen to the stopping distance? The stopping distance would decrease. If this was the line, what would they make you do in school zones? They'd make you speed up. Okay, oh, school zone ahead, I got to get up to 80 miles an hour. So in case Tim runs out, I can stop at a short enough distance. Now, you've all seen the carnage that exists out in the parking lot or on 45th. There's like a wreck every day, okay? And that's with these lines. Imagine if this was the line, like if you were going slow, your stopping distance was ready to increase, it would be a zoo, okay? It would be like a collision mayhem outside. But it would be kind of cool though, if this was mine, like you're going to try and park your car in a garage. You know, it's like pretty, small garage. It's like, oh, I got to get up to 80 miles per hour, so I can stop inside the garage, okay? Cool. But this is where physics comes in and says, okay, whatever we graph has to match the physical reality of what we're actually observing. And so because of the fact that this line doesn't match it, it doesn't make any sense. And it actually turns out to be this quadratic function right here. So faster you go, the stopping distance gets greater. And remember that when you're driving, okay? If you're out on the highway, don't tailgate someone because of that curve. As you go faster and faster and faster out on the highway, remember this curve? You actually want to keep a greater and greater distance between you and the car in front of you because of this curve. Okay. So, let me hand out that, and we'll go from there.
couldn't the dependent variable also be acceleration though? Like a slower acceleration?
No, that's the function of your brakes. That's the function. See, I got it organized, I put it away, and then I could find it. Okay, kids. So, in this lab, we're going to deal with the spring. Now, springs are pretty cool, especially if you think of kind of like a big picture kind of thing. So the cool part about springs is that they have like a memory. So if I pull this down and let go of it, it returns back to that shape. So over the years, one of the things that as a teacher, you realize and you try to pass on to your kids is the idea that Mother Nature is a lazy clean it on. Okay? Mother Nature is only going to do what is easiest for Mother Nature to do. So in my mind, Mother Nature has this big flowing like tie-dye dress and, silver hair, sits around and smokes a hookah pipe and just kind of chills out, drinks her old tea or whatever. And she's just really chill. So let me give you an example. In case you haven't noticed, organization really isn't my strong suit. Okay? I got a lot of strong suits. Keeping everything neat and tidy and put away. I'm not on the list. Okay? So let's say, God forbid, that I have to find something on this desk and I can't find it. Shocking. So there's a couple of places that I could look. I could, there's a little sink right here, right? So like if I were this thing, right, and that weight is going to fall down there. If I can't find this weight, that's where I'm going to look first. I'm not going to look and see if it's sitting up here on top of the faucet, because it's not going to randomly roll along and then jump up on top of the faucet and be sitting there. It's too much effort. That sink is the lowest possible energy state, and that's where it wants to go. So Mother Nature, being lazy and predominant, always wants to return to the lowest possible energy state. So if I pull this spring down and I let go of it, and then it returns back to that original shape, I know that is the lowest possible energy state. Because if I pull it down and let go of it, and it stays there, that means that's the lowest possible energy state. So, in effect, what happens is that spring has a memory. Now, the next question is that, what happens on an atomic level? So, even the cool thing about these being iron, okay, springs are mostly made out of the element iron. So, if you look at the kind of the history of how elements came to be in this universe, if you go back to the Big Bang about 14.6 billion years ago, give or take about 10 minutes, close. The only elements that existed first were hydrogen. You have a proton and you have an electron. Then gravity, which was like the great sculptor of the universe, kicked in. And then you began to form stars. Okay, so hydrogen coalesces in the fusion process and you get helium. So the easiest quiz that could ever be given is at the early stages of the universe, and it's the quiz of the periodic table. You only have two elements to worry about, hydrogen and helium. Okay, that's it. Those are the only two elements that exist. But then those stars conveniently began to collapse. And out of those stars, then you begin to build heavy elements, like carbon,